Okay, so this more or less leads us to the key part of today's lecture, which is the discrete time processing of continuous time signals. So this is the first of the two components. The other one will be the continuous time processing of discrete time signals, discrete time processing of continuous time signals. So I have xc of t, I have xc of t, which I want to take into the discrete domain through a C to D converter, sampling period specified Ts to avoid aliasing, produce a discrete time signal x of n, pass it through a discrete time system. We would always want it to be an LTI system where we can represent it in terms of the impulse response or the frequency response h e of j omega. So either h of n or h e of j omega, that will produce for me y of n, which I will then take it through a D to C converter, and then this will become my reconstructed signal. Notice I am not calling it x, I am calling it y because it has been processed. I may have filtered it, I may have done something to it, so it is a different signal, and x of n output, y of n, that is the input output of the discrete time system. So now if you were to encapsulate the whole thing into a equivalent processing block, if you did not know that you had gone into the discrete time domain and had just said, okay, I fed in to this green box xc of t, a continuous time signal, then I obtained a output yr of t. Okay. Now is there an input output relationship? Yes, if this is LTI. I should not do anything inside the block that violates linearity or time invariance. So if I preserve the LTI property, then I can say that this overall green block actually behaves like a continuous time filter, which is H effective, HEFF is H effective of j omega. So I cannot tell the difference between a analog signal being processed by an analog continuous time LTI system, H effective of j omega producing yr of t, and this equivalent block diagram that is happening inside. Okay, and a very interesting sequence of developments that we can study in this context, and let me just sort of give you a flavor for it. Definitely would encourage you to read Oppenheim and Schaefer chapter 4, some very interesting applications are present. So for the input output of the discrete time block, so we will have ye of j omega is equal to x e of j omega times h e of j omega, that is the discrete time LTI system. Okay. And then the y reconstructed signal yr of j omega, the Fourier transform of the reconstructed signal, will be the reconstruction filter hr of j omega times the analog representation or continuous time representation of y of n, which we have just told at the start of this class can be expressed as ye of j omega ts. It is ye of j omega. From here to here we have gone using the transformation omega is equal to omega times Ts. Okay, so basically that spectrum, it has multiple copies. The role of the reconstruction filter is to retain one and remove the rest. That is what we have here. Now ye of j omega can also be written in terms of the equation number 1. So this can be written as hr of j omega x e of j omega Ts h e of j omega Ts. And next step, further simplify or getting a little bit more insight into the signal that we are interested in. So this can be written as hr of j omega h e of j omega Ts, that is the discrete time LTI system, and the signal x e of j omega can be written in terms of the corresponding continuous counterpart, which is 1 over Ts summation k equal to minus infinity to infinity x c, basically x of n is related to x c of t, and I am writing it in terms of the spectrum of x c of t. This would be j times omega minus k times 2 pi by Ts. okay, basically scaling and the replication of spectrum, which is the relationship for this and this. Okay. So, here comes the insights that all the things that we have put together. So, let us assume that we have a ideal reconstruction filter. So, I have the ideal reconstruction filter, again do not want to complicate things by looking at the practical aspects, just for this is more of a conceptual. So, ideal reconstruction filter, immediately we recall that this has to be a brick wall filter from minus omega s by 2 to omega s by 2. This will have an height of Ts. So, this can be written in equation form as HR of j omega is equal to Ts in the range omega less than omega s by 2, but that is the same as saying this is equal to pi over Ts. Okay, so, I can equally well replace this with minus pi over Ts and this as pi over Ts. Okay. So, this is a filter that will cut off everything that is outside. Notice that even the first image of the copy of XC will be outside of this range. So, if I implement this the property here, then YR of j omega using the property of a reconstruction filter, we can then say is nothing but He of j omega Ts and only the first copy of the spectrum, that of the expression that is in green. Remember that the Ts factor has been cancelled through the reconstruction process, and what we are left with is Xc of j omega, and this is in the range mod omega less than pi over Ts and is actually equal to 0 outside, again because otherwise or outside this range because of the reconstruction filter property. So, now comes the most crucial step. Since we are saying that we are preserving linearity and time invariance, we also know the input output relationship for this block can be written as YR of j omega is equal to H effective of j omega times Xc of j omega. Okay, that is the input output relationship for a continuous time LTI system. Comparing this with the expression that we have now obtained, both two expressions for YR of call this as equation number 1, this is equation number 2, then you can write down a very important and useful result. H effective of j omega, the continuous time system, equivalent or effective continuous time system, actually is related to the discrete time system He of j omega Ts in the range mod omega less than pi over Ts equal to 0 otherwise. Okay. Just as a quick reinforcement of what we have said, let me just take this upper portion. Okay. If I were to have a discrete time filter which is a low pass filter, okay, this is a discrete time low pass filter. Now, this spectrum will repeat with a period of 2 pi. So, I will have at 2 pi, I will have at minus 2 pi, this will repeat. Now, if I map this to the continuous time frequency, that signal also will have all these copies. What the H effective filter says, only within pi over Ts to pi over Ts. In the discrete time domain, we showed yesterday that that corresponds to minus pi to pi. So, that means only what is there within this portion is retained, everything else is removed. So, I have a discrete time filter which is a low pass filter which has got periodic repetitions of its spectrum, but through the process of reconstruction I have removed the other copies, and what is left for me is only the central or the main component. So, it behaves or now behaves not like a discrete time filter, but now as a continuous time filter whose overall transfer function is H effective of j omega. So, the conditions for the LTI property to hold the discrete time system He of j omega, that has to be LTI. Basically, I am doing a transformation from x of n to y of n. The discrete time system must be LTI. The input signal must be band limited, and I must have satisfied Nyquist, because in the process of going from the continuous time to the discrete time, I should not have done anything which will prevent me from going back to the continuous time, right. So, those are the properties. So, maybe we just write it down here. So, the conditions for overall LTI, conditions for overall LTI. Again, this is very important, because you are now saying what I needed to do in the continuous time, I am actually can do it in the discrete time, provided I can satisfy these conditions. So, these conditions are very important and useful. The first one is that discrete time system must be LTI, okay, that is obvious, otherwise we cannot represent it by an impulse response, and of course, it will not be helpful for us either. Now, on the continuous time side, we have to ensure the following. One is xc of t must be band limited, then the second part of it will be that once it is band limited, that you satisfy the Nyquist criterion. Maybe having studied the practical aspects, you would say over satisfy the Nyquist criterion by a little bit, so that it is easy for us to build, because if Nyquist criterion is not satisfied, okay, if this is not satisfied, then what we will get is copies of the input signal that are aliasing, and therefore linearity will be affected. Linearity basically says what I apply at the input, there is a corresponding something that appears at the output. I should not have anything which does not directly depend on the input itself. So, if I have xc of j omega at the output, that is perfectly okay, but if I have xc of j omega minus 2 pi by Ts or some dependence on any of these things, then I have a problem, because that is not directly the input, it is a shifted version of the input. So, therefore, if any of these components are present, then I will lose linearity, and therefore, that is why Nyquist criterion is very important for us to be satisfied. Okay. So, given these, you can guarantee that the Nyquist property will be satisfied, and this is a good way for us to move forward. Now, let us build on this very quickly, because I want to make sure that you are comfortable with what we have said so far, and actually see the benefits or the power of such a mechanism. So, here is a first example, first of many examples. We will discuss this example, request you to read the other examples that are there in Oppenheim and Schaefer. Okay. So, if I have a discrete time filter He of j omega, which is equal to 1 in a range mod omega less than omega c, equal to 0 outside. Outside basically means we have to specify it, it is greater than omega c, less than or equal to pi, because after that it will repeat. So, we cannot just say otherwise, we have to say, so basically we have to specify a digital filter from minus pi to pi, otherwise it is incorrect. Okay. So, this would have a frequency response that looks like the figure that we drew, minus omega c to omega c, and then from minus pi to pi it is 0. So, this would be clearly a low pass filter, you will be passing the low frequencies. Okay. So, again it has components of the pass band, sorry, not at pi, it should be at 2 pi. So, if you extend this line pi 2 pi, we should get a copy of the signal. Again, keep in mind that we are plotting from minus pi to pi. If you were to plot from up to 2 pi, you would have to show this particular version also, and the band edges are 2 pi minus omega c, this would be 2 pi plus omega c. Okay. Keep that picture in mind. Okay. Now, I have a continuous time signal which is band limited, continuous time signal which is band limited minus omega naught to omega naught, which through the process of sampling at a sampling rate of Ts, the sampling period of Ts, which satisfies the Nyquist criterion, gives us the following. I get replicas of the spectrum scaled by the sampling frequency, and so basically there is a scale factor 1 over Ts, and they are separated by the sampling frequency. So, this is omega s, that is equal to 2 pi over Ts. Okay. And yesterday we said that once you get it into this domain, you can also relabel the frequency axis in terms of the discrete time frequencies. So, this would correspond to omega equal to 2 pi, the midpoint at omega equal to pi, and correspondingly you can look at the band edges as some pi by L or some value that is easy for us to represent. Okay, so here is a discrete time signal where you have, so now we can forget about the continuous time part, and you can say that okay, here is a discrete time signal whose spectrum is given in this by this drawing, and this has to pass through a low pass filter. Okay, so the low pass filter, let us say, has this property, and because of the discrete time property, it is going to cut it off for all of its copies as well, all copies as well. So, what we get as after the discrete time filtering has happened is the following signal. So, I get the following. I have the main copy which has this shape, and it has been cut off at minus omega c to omega c, omega c to omega c. Then at 2 pi there is a copy which is again at the same band edges. This is 2 pi, this is 2 pi minus omega c, 2 pi plus omega c, and the reconstruction process. So, now for that I need to remap my discrete time frequency back to the continuous time frequency. So, this becomes omega s once more, this and I will do my reconstruction filter, which will be from minus omega s by 2 to omega s by 2. It will have a height of Ts. Notice that the original spectrum has got a 1 over Ts representation. When I pass it through this, then I now get a continuous time output. So, y r of j omega is the following spectrum. It has the shape like this, and if you were to apply a reconstruction filter, that is indicated as shown here, a reconstruction filter that goes from minus omega s by 2 to omega s by 2, then what we, and it will remove all of the other copies, and what we will get is the signal at this point, which we can label as follows. This has a height of 1, and this is at minus omega c by Ts to omega c by Ts. And this is the overall the output response, and we will now relate this to the effective filter H effective of j omega, and this we will take up in the next lecture. Thank you.